Okay. Okay, before we start, is there any, perhaps some questions from yesterday's course? At least the double integral in polar coordinates. Okay. Okay, I'm preparing some exercise for you, but I think I will upload maybe later or maybe tomorrow. What I would like to do for today's class is basically move to the next section, which is the change of variables in multiple integrals. So I believe this is also related between how to convert from Cartesian to polar. We could also see from general perspective what we call the transformation of Jacobian or Jacobian transformation. Okay. So let's start from that sections. So let me write here. The title should be change Okay, to help you understand what does it mean, I think let me just explain a little bit. In our calculus 1, if you remember, consider calculus 1. So if we take the integral from a to b of f of x dx, we can exchange this f of x. So suppose that if we take x as another function of u, for example, we can substitute and make a new endpoints depends on these new substitutions, and make out that this will be right, and we know that this is what we call the u substitutions. So c will be, or a is g of c and b is g of d, right? Another way to write this is by taking the same integral and we can simply write f, and this is just to see the change. Right? This is what we have in u substitution, u sub method, right? So what we are observing in calculus 1, actually we see that we substitute or we exchange the variable, right? We exchange variable from dx, when we integrate, becomes u, right? Okay. Now in general, what we are going to do in our next lecture is we are going to see some general rules to transform variables. For example, any variables, for example, maybe x, y, and then we have some transformations into another variable. For example, we have done in the last session from Cartesian to polar, right? We can have some change. So just FYI, let me just write what we have done yesterday. We have this in general, and then we simply write into new region, and then change x with r cosine theta and y with r sine theta, and in this we have this r dr and d theta. Okay, now you notice something here. We change, so as long as we know the relations between this xy to new variable that we want to change, which is r theta. For example, here's x becomes r cos theta, y becomes r sin theta, and then we did some approach, and we approach through our double integral. We find that we need to multiply with this. Okay? In calculus 1, we see the relations when x, okay, we want to change into variable u, and we know that we can, maybe this will be easier to explain. Let me explain from the first one here. So if we know the relations, if x is another function with variable u, okay, and then we need to multiply with this. Okay, we need to multiply with this. So our concern is there any way, any method to find this multiplication, this multipliers, this one? Okay. So let's set some general perspective here. So if we are going to transform something like this, let's say we have two different regions here, S and R. So T is transformation. So let me write here, T is transformation from UV to XY. Okay, that's the definition for T. So we can write T UV because of the transformation, then it's become XY. Okay. And then perhaps we can relate X and Y with U and V. Then perhaps X is a function of UV. Y also the same. Let me write as G and H. Okay. Or we can also write, this is the same thing, okay, the same thing. Just in any written formulation, this will be the same. Okay. Either you choose the one that on the top or the bottom one, that will be the same. And assumptions that T is a C1 transformation, or we can say that G and H, the function, have a continuous first order partial derivatives. So if, let me move this a little bit to the left. Okay, that's good. Okay, if T is 1-to-1 transformation. Okay, 1-to-1 means that as a consequences, it will have an inverse. Which means you can see from this arrow the T inverse. Okay. So if T is 1-to-1 transformation, we are going to have an inverse, meaning that the point is exactly 1/1. Okay. So we can also write down now in terms of U and V. So U is, let's introduce a new functions. Let's say the capital G, okay, as a counterpart from the small g. That this is XY. And then V. Okay. Okay, perhaps let me go through, before we deal with this one maybe here. Let me write a little bit to the left here. Okay. Let me give you a simple example first. Okay. Let's say we have relation between x, okay, as a function of u and v. So let's say this is u plus v, and then we have y, that is u minus v, okay? And then when we transform, let's say t, we transform t uv to xy, let's say, when t is 1, 3, this will be 1 and negative 1, right? Just plug in the points, just a regular way. Okay, now we can write this xy, so let me write here. What are u and v in terms of x and y? Okay, let's say that. So let's just solve and then try to simplify from these two. Okay, we are going to write in terms of u and v. So let's say we have, I will multiply with 4, so it becomes 4x equal u plus v. And I will multiply with 2 for y, so 2y u minus v. Okay, just solving through linear equations, we get that this will be, let's say we minus to remove u, so 4x minus 2y is equal to v, or we can say v is 2x minus y. And the same way we get, if we plus, then we get 2u is 4x plus 2y, or u is 2x plus y. Now we have this new equations. So if you want to make into our transformations, or if you would like to draw, so if you would like to draw from xy to uv, so you will see some sort of transformation between all these equations. Okay, you will see all these linear equations that you can find easily. So if you want to take, so you can imagine first is you try to have x, y, and then change to u and v according to this equation. So you can check. This is both are x, u, this is y and v. Okay. Okay, now we are going to see for some next examples, we are going to see how we change from xy plane to uv plane, okay? Or from any other variables that we have the relation between those two, okay? Okay, this is just a simple example. Now I think for a little bit complex example here, as mentioned in the textbook, we are going to see here. I think I need more space. Let me just copy that to here. Okay, now if we define transformation, let's say this is our new equation that relates x, y to u, v. Okay. The picture on the left is the illustration what we have. Okay. So the the equations is find the image of S, which S has a boundary both U and V start from 0 and ends with 1. So how to start and how to process this? Now at the beginning, we could process U 0 to 1 and V 0 to 1 as this path. Okay? We start from S1, okay? Which means that we start from U, we move 1 point, V is still 0. Okay? You could also try use maybe half here, half, and 1. Okay? And then we start move to S2. Okay? From 1, 0, U still the same, constant. And then V is changing to 1. Okay? And then S3, we move back here. Okay? And then later, we move back to the original position. Okay, now imagine that we are going to transform that. Okay, we are going to transform that. So what we are transforming is this path. Okay? So this path, okay, the sides here, with U is 1 and V is 0. So let's try to look on the subject here. So when, let's say here, let's just break down this into one by one. So let's say start from S1. S1 is U is 1 and V is 0, right? Which means that in our transformation for the X, this is going to be U squared, okay? And then Y will be 0. Okay, so we take the V equals 0. Okay, take V equals 0. And then X or we take here that X is one minus V squared. Okay, so this is taken from S2. And then Y is 2V. This is, well, maybe let me write here. This is U is equal 1. And we have movement from 0 to 1, right? Or maybe this is not 1. Okay? This is supposed to be moving, so let me just write it like that. Because first we make V 0, and then we move through U, okay, from 0 to 1. Okay, that's why we have U squared as equations. And the second one, we take the 0 to 1, okay, for V, and the U will be a constant 1. Okay, so that's why we have 1 minus V squared. The V is the one that is changing. Okay, this one, V is changing, right? And then this one is just 2V because U is constant 1. And the same we can do for S3 and S4. And of course, from here, we could substitute this to here, okay, and then maybe right here that V is half Y. So we could see that in XY plane, we get that this will be will be a parabola, right? Which you can see from our slides here. You can do similar thing with S3 and S4. So S3 you can make the what's that? So we take a constant. Okay, for V is 1, and then the U is from 1 to 0. Okay, and then S4, the U is constant 0, and this is V. V is from 1 to 0. So you could make another path, okay, to see that we could also make this another parabola and then another line here. Okay. So from S1 we just move as usual, and in XY we just move as usual. So Y is 0, so start from here, Y is 0, right? And then how X move is we just move from 0 to 1, which is practically nothing happened here, so just having a line. So if you would like to completely write all the paths, so S3 we can move from this will be V is constant 1, and then U will be from 1, or right here. So X is supposed to be U squared minus 1, okay. And the Y is 2U, so U will be half Y. So we get that X is 1 over 4 Y squared minus 1, okay, which we have here on the graph. And then we can also take for the last one as 4. This is the constant for U, 0. And then we move V between 0 and 1, right? And then X will be negative V squared. And Y is 0. Okay, and then we see that it's, if we plug in here, this will be negative 1, and if we plug in 0, it will be 0. So it's starting from negative 1 to 0. So from this relations, we could somehow transform the UV plane, this XY plane, or we could also transform from XY to UV plane, as long as we know how they are relations, right? How they relate. Okay, but how we can make it in more general, in more so we could apply to all possibilities. Okay? How to find the relations? Okay? Because if we are going to do this way, then we are going to draw and then pinpoint all the positions and then draw all this. Okay. So how to do that? We first go back to our vector position, okay, and then see from general perspective through this way. So we are going to see in more general way how this transformation will affect the multiple integral. Okay, let's say we have a region S, as in a UV plane. Okay. This is the same depiction as, and then we have XY plane that has R. Then they have all given informations. The vector, okay, the vector positions. So we see the dimensions we are given for S is a small distance U, or the delta U and delta V. Okay, and then we are having a transformations that XY 0y is a result from transformations from u and v. Okay, and then the vector r uv this is a vector position. So this is r is vector position of the image point uv. Simply what this picture means, okay, if you carefully reflecting this to what we have done before, simply this is saying that all the segments is actually the segments here, okay, the transformation part. This is when u is constant, when this v0 a constant, and then it's just changed with u. This one here, u0 constant, and then v is changing. Okay. Let me write here that perhaps, okay, if we try to take the tangent vector of this r, so let's say, okay, let's say we have r u, okay, this means, or let me write, this is the tangent vector. So tangent vector tangent, or maybe when, let me write here to give you clear. Okay. When v is constant, v0, we are going to partially derive. Okay, we are going to partially derive, and I will write ru because u is changing. Okay. So this equal gu u0 v0 I plus hu. U means we are partially derived with respect to this u, and this will be u0 v0 j, and then simply we are going to derive so x to u I. Okay, so let me write first the formulation. I will explain what this is. And then tangent vector when u is u0 or a constant, we are going to have rv. Okay, now it's rv. So gv and this will be dou x dou v. Okay, now this equations, the tangent vector equations, if we try to look at what it looks like here, this is what is done. So when v0 constant, this is the tangent. When the u is a constant, this is the tangent. This is actually what we've done in chapter 14, right? We have in function of two variables, if we say the tangent vector, we are going to have two, right? With respect to x and with respect to y. This is also the same, but now we are having this v and u. Now what we are going to do from this to tangent vector is we can approximate, okay? We can approximate this image. We can approximate this image by taking two vectors, okay? By taking the area of parallelogram, if you remember, right? We can take area of parallelogram and we can do some approximation using our calculus. Okay. So we are taking as two sides A and B, okay, A and B. So taking A as R and then minus the initial positions, also B, okay, taking with this, okay, and then consider in terms of definition in partial derivative. If we take the RU, by definitions we are going to have the limit delta U going to be 0. This is definition in chapter 14 actually. So we have this definitions, right? So we could take that R minus this R. So simply we can approximate using this limit definition. This is simply we can change to delta U and RU, right? Okay. This is limit. This is limit definition of partial derivative. Okay, and then for RV, we can do the same way. And we get that for RV, this will be delta V RV. Okay, that's why now we have the picture. Now this vector can be determined by this delta U RU, delta V RV. And then we can take these two vectors, take as our parallelogram, right? How to find the area of parallelogram from two vectors? Yes, cross product. Cross product. Yes, cross product. Okay, so this is a little bit long, but the final result will be, I believe, not this complicated. Not as this complicated one. Okay, I think let me just write in another page. Okay. So let me write here. Then area, or maybe compute the area of parallelogram. Okay, let me add one more page just to add. So area of parallelogram will be described by a cross product between these two. Okay, let me write. That this equal, I will factor out the delta outside. So let me write just the vector R cross vector V. Okay. So let's compute the cross product. So RU cross RV, taking I, J, K. And let me write all the RU. Let me write maybe right here. So RU is dou X dou UI plus dou Y dou UJ. And RV are similar, but V with V. So this will be dou X dou U. This will be dou Y dou U. This will be 0. This will be dou X dou V, dou Y dou V, 0. Okay, that's okay. For the sake of computation, I will just write again. It depends on you which way you are feeling or you prefer. Okay. Usually I'm writing like this so I can get directly the result. So I get dou X dou U dou Y dou V K, and then I get minus the dou X dou V dou Y dou U K. Or simply we can write in determinants. So this determinant what we call the transformations. So this is the Jacobian transformation. So basically, this is how we can evaluate transformation between some planes. Okay, for example, XY or UV or another planes that has some definitions to another plane, okay, if we know the relations. So let me write the actual definition here. So the Jacobian of transformation. Let me just take a break and continue. Okay. Okay. So this Jacobian. Okay. So this Jacobian will be the last chapter. Okay? The last section for your final exam. So next week we are just going to review. We're going to review and have some practices. So let's continue this part here. So the Jacobian of transformation T, okay, given by, let's say we take X and y is, so we write Jacobian like this. So this will be x, y, and this will be u v. Is equal to the determinant. Okay. Is equal to now we can use this Jacobian to change our delta A in our double integral. Okay. So the delta A can be written using our Jacobian. So basically, what we are going to do is we are going to change the delta A using this Jacobian. So if this is xy dA, and we have the definitions using the sum. Now we are going to have a new relations here. So the x we change into function uv, y also change to function uv. And then the delta A can be written as Jacobian and then delta u, delta v. Or we could simply write down the integral. Okay, let me write this a little bit small. So we can write this become with the new region S. So F, G, U, V. Let me write in more detail. This is not just V, but still in the definition of integral with I and J. This is du, dv. So simply this is changing from here, from the first one here, into this Jacobian double integral. Okay, now let's review on polar. Okay. If we want to convert from xy to r theta, we get the idea that x, or now I'll write completely with the function, this will equal to r cosine theta, y is r sine theta. Now using the Jacobian, now we can take the Jacobian from xy. Now we change to r theta. Now what should we write in the in the matrix. So write this is x and r, this is x and theta, this is the y r, this is the y and the theta. So we can check from the first one, partial with respect to r. For x, this will be resulting on the cosine theta, right? So cosine theta, and then we derive cosine theta becomes negative, so negative r sine theta, and then y, we take derivative with respect to r, it's sine, and then same thing, we get r cosine theta. Okay, take this resultant for the determinant. So we get r cosine squared theta minus, right? Because of the minus r sine. So it's become plus r sine squared theta, which is, we have r. So, in conclusion, when we change Cartesian to polar, let's say we have dA here, and change to S from R, this is, let me write completely the Jacobian. And then this will be dr d theta, right? So this will be equal to and the Jacobian result is r dr d theta. And we can just add, for example, if it's evaluated from alpha to beta and a to b for the radius. Okay, so that's why it's also proven that we need to multiply with r through this Jacobian. Okay. So what Jacobian really can do is basically it can help us to compute multiple integrals. So if we know some relations and we could take that relations into simplify our formula, then this Jacobian can really be a helpful tools. Okay. Well, simply the applications you are maybe thinking in today's engineering or perhaps some software development. This Jacobian really important because they can transform some, for example, from pixel to pixel, from image to image. This transformation is really helpful to compute the formulation inside or any function you build. If you have learned perhaps some basic coding or some image processing, you will know that there will be many transformations, right? But this is the inside how they process. Okay? So we learn on perspective on how the machines read our codes and whether they understand or not, right? Okay, a quick example here, So let's say we are going to evaluate this integral. So we need to evaluate this where R is trapezoidal region, with points or vertices 1 0, 2 0, 0 negative 2, and 0 negative 1. So basically what we are going to transform is the one that we are usually looking at, the region, the area. So in the double integral, that area usually we determine with the dA or dx dy. Okay, if you see from this integration, you see that we have some complications in this exponent here, right? The power, right? We have x plus y over x minus y. And it should be obvious, okay? Whenever you see any complications like this, you see some, perhaps frequently you will see the linear equation on top of a function, or maybe inside the function you will see some complication on those linear with x, y. Perhaps that is the one that you should using the Jacobian. So you could imagine that x plus y, maybe this is another u or g or h, you can name it as many as you want, and then the other one will be x minus 1. So you could have those transformations, and we can use that and then help this to compute this double integral. And this is basically the endpoints. This is simply the endpoints. When we have all u and v within this x plus y and x minus 1, our job is to take these numbers and then we get the result for uv, because we want to exchange this xy to uv, right? Okay. So you can draw if you want, just to confirm whether you are correct or no. For example, let's say we have, so let x is, or let's x plus y, this is equal to u, and x minus y, this is equal to v. Okay. Yeah, we define, okay, we assume. Okay. And then if you want to draw first the trapezoidal region, we can do that as well. So this is 1, this is 2, so perhaps this is 2 points, that one. And then 0, negative 2 is here, 0, negative 1 is here, so maybe this is S1, this is S2, here, and then going back there. Okay, based on what we have here. Okay. And I will start from the 1, 0. Okay. Yeah, you can try the one that we have before and then try drawing, but I will just directly give you the how to solve this basically in the double integral. So let's solve this. So in terms of x, y, so let's find, so let's take minus, so to y, we have u minus v, or y is half u minus v. And then if we take plus, we have 2x equal u plus v. And we have x half u plus v. Okay. So we have now relations in terms of x and y. Okay. And it's mentioning the uv. But I think you need to draw this, I think. There will be some tricks in the last part. But let's just find the Jacobian first. Okay, let's find the Jacobian first. So the Jacobian, based on these two equations, so we start changing variable from xy to uv. So let me just write, just to help you remember what this is. Okay, so for both, we just have half, and this is just a linear equation, so half. So first one is half u, the derive is become half. The second one, v, we derive, it's negative half, because it's negative half v. And then this one will be half. Oh, sorry. This should be positive. The negative one here. I'm switching the xy. Sorry. So this will be resulting in negative 1 over 4 minus negative 1 over 4, which is negative half. But this is going to be inside the absolute value, remember, in Jacobian. So we have half. Okay, so based on this xy, so this is xy. So if you want to take into u and v, we get that x or u is x plus y, v is x minus y. So we exchange all these points. Exchange this, and it becomes, so 1 0. Okay, so 1 0, u is 1. Okay, and then x minus y when x is 0, and when x is 1, so this will be 1. Okay, and then, or maybe let me write it more clear. This is going to be here. Okay. And then this is going to be the transformations. And then 2 0, we get 2, and then v is also 2. Okay, and then 0 negative 2 for xy. So 0, so negative 2, and then negative is positive. Okay, and then 0 negative 1 is negative 1 and 1, right? Okay, now let's say this is yx, right? And let's say we are going to have u and phi. So this is u, this is phi. So first is 1 1. 1 1 is, let's say 1 1 is going to be, this is 1, this is 2, 1 2, 1 2. So 1 1 is here, and then 2 2 is maybe here. So that's the first one. And then negative 2 and 2. So this one here. So this is, let's say, what should we write here? Let's just say S1. S1. And this part is S2. Okay. And then we have another one here that is S3. And another one here, which is the S4. Why we need to do this? Because we want to make sure that if we can define this uv as a constant, we can directly write inside our double integral as a constant. But if we see something like this, then perhaps one of them are functions, right? And we see here, what is this? From perspective of this graph U and V, this is practically U equal V, right? Okay, because it's 1, 1, 2, 2, and the other one is U is negative V, or V is equal U at the same. Okay. So we can take the constant as V, because it's easy to find from this part goes here, right? And then the functions will be from this one to this one. Okay. So we could write. Okay, we could write first. We could write the conclusions first based on the Jacobian. So this is R. So this is simply, let me just write S first. This is E U over V. And then Jacobian, let me just write Jacobian first. And then du, let's say dA. Okay. So we have this U over V. This is half. And then we want to make V as a constant, right? So we can take du dV. So V, let me use different color, from 1 to 2. And then what else? From the left part, negative V to V. Okay. And then as usual, we can take the inside integrations. And I think I will need a new page because no space now. So not yet finished. We still have to complete the integrations. Okay. But the idea is the Jacobian is here. So sometimes the type of questions they are giving you some points to be visually determine how the transformation will be, or perhaps they will give you some equations directly that you can use. Okay, let's I think let's solve this just to refresh our integrations method. Okay, so we can start by taking half, going there, and then take this as outside integrations. Well, let me just write all the things down first. Okay, we are going to take this with respect to U. So if this is, so we have, let me write here. We have E U V du. So we take V as a constant, right? We take V as a constant. So if we take V like that, if we take the integration, yeah, then this is the integral. So this will be V E U over V. and then negative v to v dv. Or you could try substitutions, or just, I think if you are already sometime in integrations, if we went back to our calculus 1, we could try some guessing method, okay, and then you try to differentiate whether it will be your integral or not. Okay. That also can apply it here. Okay, so this will be half. So we put v, so that's v, e, and then minus e minus 1, right? dv. And e can put outside, and this will be half v squared from 1 to 2. This will be 3, so this will be 3 over 4 e minus 1 over e. Okay, perhaps some other example. Okay, I will give you another example. Okay. Okay, this example here. So we have, okay, find the Jacobian. I think you can do it, right? You can do it, right? Just find the Jacobian. I think you can do it. I think you could see number 17 or 18, okay, if you are wondering. And it is giving you some vertices, some region for the vertices. And you are given the transformations. It means that you are going to use this transformation for this x minus 3, 1. So you are going to transform using this x, y equation. And the same thing with the number 18. You have this transformation. So you are going to change this part into this equation. So this is more like direct questions and giving you the instructions which equation you should take for the Jacobian. Okay. You could try to draw, for example, number 17 is the triangle. Start from 0, 0. Okay, so we have 2, 1 maybe here, and then 1, 2 probably here. So we have this, that, and this. Okay. So perhaps this is going to be the path. Okay. And we could find the Jacobian through this equation. So we can find Jacobian directly. So dou x dou u is 2, dou x dou y, dou x dou v is 1, dou y dou u is 1, divided by v is 2. And we get that this should be 3. The Jacobian is 3. And then the computation, we need to take x minus 3y. X minus 3y is equal 2y plus v minus 3u plus 2v. So this will be minus u minus 6 plus 1 minus 5v, right? Okay, so we have now x is 2u plus v, y is u plus 2v, and then we take 0, 0. Let me check while. Let's take 2. Let me move this. I will move this to down here. And then the same way. Okay, now we change the 0, 0. This is still 0, 0. What's supposed to do 1? So 4 minus 1 is 3, so it's 1, and b is 2. Minus 1, 0. Yeah, 2 minus 2, 0, yeah. And then this will be, what will be this?
0, 1.
0, 1. Oh yeah, 0, 1. Okay. So we could transform this. Zero, 0, 1, 0, and 0, 1. So here. So S1, S2, S3. Okay. And then what next is to change the double integral. It's R. And then let's say this is U, this is V, right? This is X, this is Y. This is 1. This is 0. Okay. So we can take this dv. Okay, we'll take dv from 0 to 1. And then what this will be? This will be v equal 1 minus u, right? Or u is 1 minus v. Okay. We can take v or u, depends on which way you are going to do. So if I take v equal 1 minus u, so this will be from 0. So this will be dv du. So negative u, negative 5v, 3, okay, and then dv du. Or you could, if you want, you can make du dv, then du dv, zero, 1. I think the same, right? And each way you will get the results, okay? You can just compute. If you want to compute, perhaps you can compute first, as usual. Maybe let me just erase the below here. So you can compute the inside integrations. So we are going to take outside. So this will be negative u, or maybe let me write negative outside. So this will be positive. So uv plus 5 over 2v squared. Take from that. I think we still have more to complete, but I will just end up till there. So I hope you can get completed. I think it's a normal integration, but you need to square this and then integrate once more and then finish. Yes, we have squared here, right? We have of d. Yes. Okay, I think that's it for today. Next week we are going to review. Okay, we are going to review. I think I will emphasize more on chapter 14 and 15. Okay, because I believe you are already forgotten chapter 14, right? And a little bit of factors. Okay? Okay, that's it for